Okay, hello everyone. Last talk of the day. We are a bit late. I have tons of slides. This is a 1 hour talk. I'm gonna try to fly through them and hope that my battery lasts long enough because Linux sucks. Anyway.
No one has anything else to do tonight, so you can go as long as you want.
Yeah, sure. So anyway, thanks for coming, by the way, and for sticking around. So this is my talk, big match, how I learned to stop reversing and love the strings. My name is Paolo Montesel, and whatever, my nickname is Babush. Abstract, okay, so we have all been there, right? You reverse a software for a while and you realize that you're looking at open source code. That happened to me a lot. Why? Because maybe you didn't copy-paste the right string into Google. Or maybe Google wasn't good enough. So me personally, but also the company that helped me do this, we asked ourselves, can we not just like build a giant database of all the strings on GitHub and stop this stupid thing from happening? I will tell you about it, but first about myself. I come from the northeast of Italy. I'm self-employed. I like reverse engineering, data science, machine learning, and other stuff. If you know mhackeroni, that's my CTF team. We just won hacking a satellite. I didn't do much. I just took videos and made media on Twitter, but if you saw the video, I'm the guy that did them. But yeah, we won. Not DEF CON CTF yet. We're not good enough. This work was done while I was contracting with a company also from Italy called Revenge or Revengi. Call them how you wanted. They're a company. They're building the compiler based on LLVM, and they also do binary analysis, reverse engineering, and they're very, very skilled C++ and LLVM consulting shop, if you need that. And yeah, Big Match was kind of my own research project there. So, life of a reverser. You open a program in Ghidra because you don't pay for IDA. You copy-paste it onto Google. You find, hopefully, some code on GitHub that matches what you're looking at. This is not the same font that was, I don't know. Anyway, and you're happy, right? Other variation of that, you can use grep up, which is very, very nice for code search. You can use, now there's GitHub code search, sorry. You got GitLab, SourceGraph, and if you know any other tool like that, tell me. I'm always looking for stuff like that. Why strings? It might be obvious, but because they are easy to see, easy to search for, they are compiler independent, so it doesn't matter what flags or what, if you use like GCC, CLang, or whatever, the string is gonna stay the same. Maybe the encoding is gonna change, and they're platform independent, so you can use them in if you compile for a mobile target or x86, they still work the same. And they rarely change during the lifetime of a library or repo, which is pretty nice. Let's start with the story that started this whole project. So it's 2018, and you just graduated from university, right, in Italy, and you need money because you're poor while you're looking for a job, for your first job. And your uncle, like your families try to make you help your uncle harvesting grapes, which is the worst job I've ever done in my life. It's 10 hours a day under the sun in August. Not nice. And you read that somebody found some like very trivial buffer overflows in Line, very popular messaging app that you know here in Asia, I guess. Especially in the voice over IP stack, which used to be implemented in a library called libamp.so. So, yeah, given the choice, it's bug bounty time. So again, life of a reverser, this is actually a string from the target that I was reversing, libamp. You find out that they're using this library, which is called libsrtp, for whatever reason, and you're happy, right? Not really. The reason is static libraries, right? So if you choose the wrong string from your target, you might be missing out on the outer library, so you're actually still reversing open source code, even though you found that there is one library that is open source. Maybe you missed maybe you missed this one, which is actually pretty big, which is called pjzip. And so you're still actually reversing open source code, and I personally wasted 1 week before finding that out because I copy-pasted the wrong string onto Google. So yeah, this is what happens. You find the library and it's the wrong one and you waste a week. The problem is strings are not perfect. You got nested statically linked libraries. Maybe the parent library is still open source, but it doesn't have any string or any magic value that you can throw on Google. Maybe the string is not unique enough, or maybe it's too weird, so Google doesn't really index it properly. And now Google search is going AI. So if you throw strings, it doesn't return anything. Google Images actually is more helpful in that for some reason. And yeah, also obfuscation, but we are going to ignore that. Doesn't exist. So this solution is obviously to build a huge database of strings. So you scan all the C and C++ project on GitHub, you harvest the strings, you throw them in a database, somehow query the database using a binary, and save a lot of time. But there are many problems. It's not so easy. First of all, you need to download stuff from GitHub at scale. You need to parse C and C++, which is hard and very slow. You got several versions of the same library. You've got Linux having like 50K plus forks, and every time you download it, you waste a bunch of time just downloading it, and then you need to parse it. And in the end, even if you do all of this, how do you score the result? How do you query the thing? Also, this was a personal project that was done as a 20% kind of thing. So we wanted a proof of concept to prove that this approach works. So I had limited resources, and I wanted to keep it as simple as possible. So this is actually our solution. This is the outline. So yeah, we downloaded the top N most starred project C and C++ projects from GitHub. We deduplicated the repositories as much as possible so as to remove unnecessary stuff. We extracted the strings, de-escaped them to turn, for example, \n into the actual character, hashed the strings and did perfect matching, more on that later, stored them in a database, queried the database, and then clustered the results. We're going to see why that's actually very important. For the dataset, pretty easy. You query GitHub APIs for projects, sort them by stars, and you clone them, right? You got rate limiting, you got bandwidth problems, and you got time. You don't really want to waste like months downloading everything from GitHub. Enter GitHub Torrent. This project started by a professor at TU Delft in the Netherlands in 2012. What they do is poll continuously the GitHub public events API. And for every event, for example, an event might be like a commit. You get a commit and you get a JSON file with a commit diff and who did it and what project it belongs to. They did this thing that GitHub Torrent, that once you get a commit, they look into, okay, do we have the repo from which this commit comes from? Yes or no? If they have it in the database, doesn't matter. If they don't have it, they actually poll the project itself. So they kind of create a SQL-like view, like database-like view of GitHub. Of course, it's missing data everywhere, but it's still the best thing that you can actually run on your laptop. And they make it available as a MySQL or a MongoDB dumps. So yeah, this is like their schema is pretty big, but you can see like this is a user, this is a project. You got this edge is a fork, so you can know if a project is a fork of another project. You got the commits and if they belong to this project. So it's quite helpful to do some data analysis before actually cloning the repo. And the nice thing is that you can actually, it's of manageable size. You can download it. You can run query locally in SQL. It's very easy. You can filter pretty easily. And you got all the metadata you need to assess like forks, commits, and the start. So basically, most of the stuff we needed was in this GitHub Torrent project. The bad part of it is that it's best effort. So as I said, they keep polling the GitHub API, which means they cannot possibly have every info about every project on GitHub. But hopefully, by virtue of random chance, they got the most important ones anyway. And yeah, some missing outdated data. There is no source code, There is like the diff information on commits. And also it looks like the project is currently dead. The domain doesn't go to anywhere. I checked like yesterday. Because this project actually, as you can guess, requires a lot of money to run and people. And Microsoft used to sponsor them. I wonder why they stopped. This might be the reason. Microsoft actually bought the whole thing, so they don't care anymore about GitHub Torrent. In the end, we went with the Mongo dumps because while the SQL was very nice during while we were messing with the data, it's actually too slow and we don't need much information, we don't need all the tables. So it's easier to write a custom Python tool that goes through the whole thing and we just dump whatever we need. And you can do that with PyMongo to parse Bison, which is like the binary version of JSON. Okay, so we got the data. Thanks to, like the metadata, thanks to GitHub torrent, it's time to talk about repo deduplication. So as said before, we don't want forks. The first 100K repos from GitHub, like the top start C and C++ repos, amount to like more than 1 terabyte of gzip source code. This is without any Git history. This is just like the zip. So that's quite a bit. There are more than 100K projects on GitHub, and you don't want to waste hard disk. Also, I don't know if any one of you does any data science stuff, but every time you got duplicated data, it ruins your accuracy. And there is a problem that GitHub torrent does give us information on forks, but only forks created through the fork button on GitHub. Because if you just push Linux on GitHub, it's very hard to know that that's actually a fork of Linux. So yeah, sad face. Even more problems is if you want to deduplicate stuff, how do you really define an individual project? What is like different enough that you consider it a different library? For example, is AFL and AFL++ two different projects, the same project? It's hard to define. And also we got monorepos like FreeBSD that they just dump every source of every library they use inside the same, as a source dump in the same repository. And we decided to create our own kind of stupid algorithm using root commits. A root commit is a commit that's like the first in your history. So you can do git init, git add, git commit, and that's your root commit. So yeah, instead of relying, like on top of the information that GitHub torrent gives us on forks, we implemented this algorithm, which like in theory would work like this. So you clone a repo, put every comment in a giant graph database, and then connect parent and child commits, and repeat this for every project on GitHub. And then you look for every root commit, which you assume is an individual project. And for every root commit, you just keep the most star, because we are assuming that if a project has more star than another, and they have the original commit in common, probably you want the one with most stars. But of course, this is impossible to do in real life. So again, we have a workaround for a workaround algorithm, which is go back to GitHub torrent, because we want to deduplicate before cloning, and to have history of everything, you need to clone everything. And we also wanted to strike a balance because you don't want to deduplicate too much, otherwise you throw away stuff that you want. But also, if you don't deduplicate at all, you keep all random forks of Linux that we don't really care for. And we thought this root commit thing was a good idea using like GitHub torrent, but yeah, people, can I swear? Yes, no, okay. People do read something with their Git history. This is time for the second story. So, I don't know if anyone here is familiar with Octocat Spoon Knife. It's a very popular repo. I never heard of it. Apparently, it's linked, like, it's the GitHub tutorial for forks. So that's why it's popular. If you follow the GitHub tutorial on Git, you more likely than not, you fork this project. More forks than Linux. And this is the history of LibreCAD. You might notice something weird here. There is a Octocat right here. You might wonder why, and because this guy called You Are Funny, a GitHub user, took Spoon Knife, the tutorial repo, forked it, then took LibreCAD, forked it, and then he decided to merge the history of both projects in the same Git repository for some reason. And this is not he opened a PR for LibreCAD, and he got accepted. So now the history of LibreCAD and that stupid repository are linked. And if you don't believe me, that's the commit that you can check on GitHub. And you can see that it's Spoon Knife inside of LibreCAD history. It doesn't make any sense. Why is that a problem for us? It's because now we've got LibreCAD, which is a popular repo that we would like to include in our analysis, that has 2 root commits, but Spoon Knife is more popular as far as stars goes. So our algorithm will throw away the repo we actually care about because of some guy that did something weird. Yeah, I hate my life. So in the end, we decided, okay, let's do the best we can do. Let's use GitHub torrent. It gives a partial information of parent and children commits and which repos they relate to. It's not perfect, it's not complete, but let's see what we can do. And this is the algorithm. It's a bit complicated, but I've got some examples. So we start by finding commits without parents. We call them parentless commits. And this is without parents because GitHub torrent either doesn't have information or they are root commits. We don't know. We create this huge history subgraph following only the parent to child edges. Yeah, this is going to be difficult to follow. And we group all repos associated with that subgraph in what we call a repository group. And then for every one of these groups, we take the most star repo, which will be considered the parent. The others will be the children. We do that for everything. And in the end, we just keep the parent repo. This is too complicated. I know that was hard. So here's the example. This is like a subgraph of the history of some commits of some project. And you can see GitHub torrent might give us like, okay, this commit D is contained into repo 1 and repo 4, C in repo 2, repo 3. Some partial information on the history of the project. So we start from the first commit without a parent and just go upward instead of also considering E. So we just go up and consider like child commits. And we group them in a group of repositories. Then we do the same for the other parentless commit. And for every group, now we know the stars, how many stars they have. We take the repo with the most stars and consider it the parent of the other. And even if it's not true, that's the best we can do. Then we do this, like these are all the repos, parent and children, and we just keep the repo that doesn't have any parent. So this is our way to deduplicating the stuff. It's not perfect. We found out by looking manually at the data that it's kind of good enough to keep what we wanted to keep. If you have better ideas, please let me know. Then we need to process the repos. Parsing C and C++ is hard, and we didn't really want to do it. So we just went with grep, grep, which is a very fast implementation. It works very well, and it's good enough for our purposes. To de-escape the strings, we used a library that I wrote. It's very stupid Python. Because, yeah, there are many ways to treat strings so that you can then match them. Any choice you make is going to give you a different trade-off. We decided to just de-escape and not worry about encoding at this point. And then we just hash them with whatever hash you want. Then we need to polish the data. And, yeah, so search engine 101. So the query system actually works using a vector space model, which now was made popular kind of by vector similarity with AI and deep learning, but this has nothing to do with, like, it's the same concept, but there is no machine learning involved. So what you do is you have like two documents. So one is, hello world, my name is Babush, and the second one is, good morning, Babush. You throw them in a vector, you vectorize it by splitting the words, and if the word is present, you put a 1. If the word is not present, you put a 0. You do the same for every document you have in your collection. And then you calculate a similarity between the two vectors. There are many ways to do it. Doesn't really matter. They mostly work the same. So why this? Because if you think about it and you swap documents with repositories and you swap words with string hashes, we can actually build a search engine for GitHub repositories, kind of. And the idea is that you take the strings from your target and pretend it's a new repository, and then look for the most similar repository in your database. And of course, at this point, we needed to build a very advanced ETL data science pipeline. So we went with Bash. It's all Bash. Not my choice, honestly. I was told to use Bash. Hi, Alessandro. It turns out in Bash you can do a lot of stuff, like even joining tables, you can do that. You can join files in Bash once you figure out how to make it not mess up the encoding. Yeah, so this is actually a visualization tool that we built to debug when it was going wrong. Anyway, so vector space model, pretty easy. It still requires us to make some design decisions. So for example, like which weighting scheme and which scoring algorithm, formula to use. For this, we built a synthetic data set using Gen2, which allows you, as you know, to like build libraries from scratch. And you can tell him to build a static version of the libraries. So we kind of had a ground truth because we could build libraries, extract the strings from the libraries, and then we knew which libraries they came from, which is very helpful. And long story short is the best weighting scheme we found was TF-IDF, which is very common for search engines. And a scoring cosine similarity, which is also like the most popular choice. Easy enough. We also wanted to remove useless strings because we found out, like, you know, the string error is in every project on GitHub everywhere, and that means you throw in a lot of results that are not really related to what you're looking for. So you get lower accuracy. And by testing with our synthetic dataset, we found out that removing the top 10K most popular strings was actually was a sweet spot in improving the query results. And if you wonder why we plotted the thing, so here you got the strings sorted by popularity. So this would be like the first string, like let's say this is error, and this is like, on this you have like the most random string ever. You can see that around 10K, which is here, there is kind of a knee in the distribution. Like this is black magic. This is not really science, but like the numeric analysis told us that this was the sweet spot. And by looking at the graph, you can see that there is like a huge decrease here. This is a log-log graph. So we decided to remove everything to the left of this. And as a double check, we wanted to see if some common string that is still interesting, like GIF89A, which is the magic number for GIFs, was still in the dataset. And it was here, like in the intercept of this line. So hopefully this was clear enough. But anyway, by removing the top 10K strings, we still had many strings that we cared about, like JPEG and GIF. So that was good enough for us. But we were still having bad results because we still have some forks or some different version of the same libraries passing through all our, like, the duplication stuff. And so you would get maybe your project, your target that inside repo A, and then you would get in the results all the forks of it before reaching the second library contained in the target. So yeah, let's say you've got zlib and libssl in the same binary, you would get zlib, 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 and then like the 100 result would be finally libssl, which is not really a good search engine if you ask me. Enter spectral co-clustering. We tried many clustering algorithms. This one worked magically, apparently. So this is a graph of the search result, actually. So we queried using the strings from a target. And here you got, on the y-axis, you got the repos that match any of those strings. And here you got the actual strings in our database. And every red dot is a match. So it means that that repo has that strings. After clustering, you can see like these diagonal blocks. You can even eyeball them. They are like independent libraries because they all share the same strings more or less. So we use this fact to cluster the result. So putting everything into production, the search engine part is really stupid. It's just like a matrix multiplication between the database and the query vector. Pretty standard, very memory efficient. But before actually publishing this, we did a second deduplication step because we found out that we were using 40K of RAM per repo on average. That's a lot. It means that there are some repositories that have used too many strings. And yeah, the average string count was like 23K. So it means that on average, a repository in our database had 23,000 strings. That's not common. So we wanted to remove even more stuff. And the way we did that was with a very stupid deduplication algorithm also implemented in Bash. So the idea was you take a repo, you look for repos of similar size, and by size I mean literally like the zip file. You unpack them, you look for the similarity between the strings in one and the other, and since similar repos are more likely than not to be close in size, you can actually use this simple, like this algorithm, if you were to apply it to the whole database, it would be n squared, which is not tractable, but you can do something similar like that and exploit the locality of the size of similar repos and do a simple like Jacker similarity. It's just a stupid similarity score. If it's higher than a threshold, you just delete one of the two. And this actually took care of a lot of like Linux forks, Android, you name it. Especially big repos were removed using this. It's time for a demo. I didn't take too much time. So this is the demo we published. And the idea, yeah, is you browse. I got my libamp from 2018 here. The web page grabs the strings in a like strings like the string command, but it's implemented in stupid JavaScript. And this is the results. Of course, I chose the proper example for it to work because I'm a scientist. But yeah, you can see like the first results is actually pjzip and some other like forks of pjzip. You get the stars here and you got the similarity score. And then the second result is not pjzip anymore, but it's like some other stuff, like it's probably lib2m crypto and a JSON parsing library. So when it works beautifully. But yeah. Yeah, that's the idea. I mean, it's not sure, of course, but you're very likely to have the top clusters library into your target. Of course, you need to double check then, but don't try with too big, like files that are too big, it's gonna fail. There is a check for that. But anyway, it works very well if you have good strings, of course. Almost done. Yeah, so this is our approach, and the pros are that we wanted to try like something better than perfect strict matching like we are doing right now with hashes, but actually perfect strict matching works good enough, kind of. So for our MVP, let's say, and it's also nice to use hashes because we don't really know what you're sending to the server. You're not sending like the binary; you're just sending the hashes of the string. So unless we have a match, we don't know what project you're looking at. And there is 0% machine learning, which is my pride. Yeah, of course, this only works with targets with good strings. That's life. And yeah, we don't do partial matching. So if your decompiler or whatever make a mistake in the prefix, we don't get any match because it needs to be a perfect match. The query speed is good enough. It's a POC size database. I think it's around like 80K projects right now. And yeah, we are using like a strings-like approach to extract strings, but in the end, you would do this as a plugin for the compiler and extract the actual strings using pointers and stuff. The idea for this project was to be like included when Revenge, the compiler, is not released yet, but when it will be released, hopefully this will be one of the features. And yeah, do some partial string matching. Also, there is no difference between magic numbers and strings and constant arrays. Really, any constant value that you have in a binary would work with this approach. The problem is, more often than not, constant values in C programs are defines, so you cannot really just grep. You need to probably compile, but surely parse the program, which It's doable, but requires more time. And yeah, another idea we got was to use strings to guess a version range of a library. So if you have a firmware, a blob, you can find that they are using libpng, and maybe this, or whatever, maybe a better project that has more strings, they have more strings. But you can actually use strings to kind of guess which version of the libraries you're looking at. And then you can drill down with the actual GitHub repository to see the exact version. But you have a first approximation. And also, yeah, nothing prevents you from actually decompiling stuff and throwing in your own strings or constant values. I actually have implemented, as a personal project a few months ago, a version that does parse C and C++ files, and I have now per function strings. So that means that if you're confident enough that a string is unique, you can automatically rename it in IDA or whatever, which is pretty nice, I guess. Yeah, another thing that we found is that it's very nice to find out in monorepos which, even without looking at binaries, but you can use strings to guess which libraries are included in a monorepo, even if it's just a single file, a single C file. It's very nice, and those might not get picked up by GitHub vulnerability scanner. So you could actually use something like this to find outdated dependency into big monorepos on GitHub. I have a friend that works for a big company that does malware-related stuff, and he told me that he used this kind of approach for malware classification, so that also works. And yeah, of course, you can try to use it on other languages. As a happy ending, Line did give me some money, so props to them, and I did not have to do manual labor. So I'm happy about that. Some more slides? Not really. Thank you. That's the original blog post. If you want to read it, it's just a more textual version of this. You got the demo, my website, and some stupid videos on YouTube if you want to follow me. Thank you very much.
Thank you. Guys, all the slides are online immediately after the talk. So no need to take picture. Just go to the website for Hack in the Box. You will find the full slide. Any questions? Yes.
GitHub torrent. It was running until at least the first year of COVID, which would be 2021. They were 2020 or 2021. I was using it for another thing, and it was still being released. They might still have the dumps if you ask them. I didn't check. I honestly was surprised when I went on the website and the domain is not registered anymore, but surely they saved them. Sorry, and there are similar projects that do the same kind of thing, but they're not as good as this, so we went with this. Yeah, I mean, after we did the POC, it wasn't updated because I'm not working with them anymore. And they are focusing on the consulting to bring in the money and on the product. This would be a feature of the product, so you need a product in order to have the feature. But yeah, I'm trying to see if I can do the per function thing. I'm trying to do it myself, kind of, and I will publish it hopefully during the next few months. But yeah, thanks a lot. Thanks, guys. I know this guy.
Yeah, thank you. How long does it take to build a search database?
I don't really remember, but it was in 1 day or something like that. It's very Bash. It's really, really fast.
Yeah, I believe that. And
it's just very painful to work with.
And do you get any advantage, say, if you want to do almost real-time incremental updates to the database? Is there any sort of caching that could cut down the time, from 1 day to maybe if you want only to add the last week worth of commits?
You could do incremental updates up until some point, because when we vectorize the stuff, we need to know the whole superset of strings that you're going to find, kind of. But yeah, So up until some point, you can cache.
Can't we just use GitHub search to find the most common string found in, no, not most common, least common strings found in the, like when you upload a SO file, right? You uploaded a library, right?
Yeah.
So then it finds out the strings and then it just hashes it and then sends it to the search engine. So why can't we just search those strings which you are sending it in GitHub directly? Like, can't we search that strings in GitHub, which will use GitHub search directly?
Yeah, you can do that. Problem is, you don't know, like, you're gonna get some, like you said, first of all, you need, the difference between that and what we did is, with this, you're querying all the strings at the same time. I'm not aware of the fact that you can do the same on GitHub.
Like, there is a new GitHub search called GS GitHub search.
No, yeah, I know, but you're still searching for one string.
No, GitHub code search, you can give a OR. Like,
okay.
You can give quotes or, and you can give multiple words with the OR in between it so that it will find all the repos with all those strings.
Okay, I need to check that out. Still, I wouldn't know how they score but yeah.
We can.
I mean, sure, you can also like use APIs to search the strings and do some clever trick to see if the repo is actually what you want. But yeah. Thank you.
Any more questions? Okay. Thank you, Paolo.
Thanks a lot.